We spend a lot of our lives trying to predict the future. We're checking the weather, we're trying to pick stocks. But what happens when the stakes are way, way higher? When getting the prediction right affects millions of people? Well, that's what we're going to dive into.
So I want you to just think about that for a second. Seriously, if you had to predict something incredibly complex with tons of moving parts, where would you even start?
Because for the folks managing our power grid, this isn't some fun thought experiment. It's a real, high-stakes question they have to answer every single minute of every day to keep our lights on. And if they get it wrong, well, the consequences are huge. And that gets us right to the heart of what we're talking about today, the power prediction problem. How on earth does a power plant know exactly how much energy it's going to generate in the next hour? I mean, it is a total balancing act. If they produce too little power, you're looking at blackouts. Produce too much, and you're not just wasting fuel, you could actually damage the grid. The margin for error here is razor thin. So, what makes this so tricky? Well, it all comes down to the environment. For this type of power plant, its efficiency is constantly being nudged around by these four things: the temperature outside, the air pressure, the humidity, and even the vacuum pressure in its own exhaust system. They're always changing, and each one has a subtle effect on how much power gets made. So to crack this puzzle, a team of data scientists basically had to become detectives. They weren't looking for a culprit, though. They were hunting for clues hidden deep inside thousands of hours of data. All right, so here's the case file, so to speak. The evidence? Almost 10,000 hours of sensor readings, tracking those four environmental clues hour by hour. And the mission? The whole goal is to use that data to perfectly predict the net hourly energy output, which the engineers just call PE. So the first clue they looked at was air pressure versus power. And yeah, you can see there's something going on, but it's a mess, right? It looks more like a big fuzzy cloud than a clear line. Not exactly a smoking gun. Okay, so air pressure was kind of a bust. What about humidity? Let's take a look. And nope, same story. Just another scattered mess of data points. If you're a human looking at this, it's pretty much impossible to find a clear pattern. The trail seems to be going gold. Now, the detectives knew the answer had to be in there somewhere. All the clues were on the table, but the connections were just fuzzy. But then, they plotted the one variable that changed the entire game. And bam, there it is. This is that aha moment you always hope for. When they graphed the outside temperature against the power output, the connection was suddenly crystal clear. As the temperature goes up, the power goes down. It's clean, it's strong. This was the key. This was the clue that cracked the case wide open. Okay, so once you have that bombshell clue, what's next? Well, you stop being a detective and you start being an architect. It was time to build a model that could look at all four clues at once and make a prediction. It was time to build a digital forecaster. And they followed a pretty classic game plan for this. First, you explore all the clues in your data, which is what we just did. Then, you train a bunch of different predictive models on that data to see which one gets the best grades. And finally, you pick the winner. And the winning model was a random forest regressor. I know, it sounds super technical, but the idea behind it is actually pretty brilliant and kind of simple. Just imagine asking thousands of different experts for their prediction. Each one looks at the problem a little differently. The random forest just takes all of their answers and figures out the smartest possible average. So that all sounds great on paper, but here's the real question. How did this digital forecaster actually do when they put it to the test, with brand new data it had never seen before? Let's check out the results. First up, the accuracy score. And wow, 95.9%. What that means is the model could explain almost 96% of the changes in the power plant's output just based on those four weather variables. In the world of data science, that is a straight-up A+. It means the model really, truly gets it. But a percentage is one thing, right? What does that mean in the real world? Well, the average error for its predictions was just 3.46 megawatts. For a huge power plant pumping out over 400 megawatts, being off by only 3.5 is an incredibly tiny and incredibly useful margin of error. And really, this slide just says it all. Look at this journey. On the left, you've got that confusing, chaotic cloud we started with. It's just noise. And on the right, that is clarity. That's taking all that noise and turning it into a confident, reliable, and super tight prediction. Let's zoom in on that proof because this is so cool. Every single dot you see here is 1 hour of operation. The bottom axis is what really happened, the actual power produced. The side axis is what our AI model predicted would happen. A perfect score would land right on that diagonal line. And just look how tightly packed those dots are. It's almost a perfect match between prediction and reality. Okay, so we've got this super accurate model. So what? Why does a project like this actually matter in the real world? Well, it's all about building a smarter, more stable energy grid for all of us. And just to close the loop on our little investigation, the model confirmed what our own eyes suspected. When the AI ranked all the clues by how important they were, what was number 1? Ambient temperature. That aha moment was legit. The machine learned that temperature is the single biggest factor. And this right here is the whole point. This isn't just a cool chart or a fun experiment with numbers. This is a real, practical tool that can help power plant operators plan better, cut down on waste, and make sure the grid stays stable and reliable. It's AI doing something truly useful. And that leaves us with this one big, exciting question. We've just seen how AI can find a clear, predictable signal inside a bunch of noisy data to help run something as vital as a power plant. It really makes you wonder, where else can this exact same idea help us build a more efficient, a more predictable, and ultimately a much smarter world?